Sintering is the process of compacting and forming a solid massive material by heat and/or pressure without melting it to the point of liquefaction. Sintering happens naturally in mineral deposits or as a manufacturing process used with metals, ceramics, plastics, and other materials. The atoms in the materials diffuse across the boundaries of the particles, fusing the particles together and creating one solid piece. Because the sintering temperature does not have to reach the melting point of the material, sintering is often chosen as the shaping process for materials with extremely high melting points such as tungsten and molybdenum. The study of sintering in metallurgy powder-related processes is known as powder metallurgy. An example of sintering can be observed when ice cubes in a glass of water adhere to each other, which is driven by the temperature difference between the water and the ice. Examples of pressure-driven sintering are the compacting of snowfall to a glacier, or the forming of a hard snowball by pressing loose snow together. The word sinter comes from the Middle High German sinter, a cognate of English cinder. General sintering. Sintering is effective when the process reduces the porosity and enhances properties such as strength, electrical conductivity, translucency and thermal conductivity. Yet, in other cases, it may be useful to increase its strength but keep its gas absorbency constant, as in filters or catalysts. During the firing process, atomic diffusion drives powder surface elimination in different stages, starting from the formation of necks between powders to final elimination of small pores at the end of the process. The driving force for densification is the change in free energy from the decrease in surface area and lowering of the surface free energy by the replacement of solid-vapor interfaces. It forms new but lower energy solid-solid interfaces with a total decrease in free energy occurring on sintering 1 micrometer particles or 1 cal per gram. Decrease. On a microscopic scale, material transfer is affected by the change in pressure and differences in free energy across the curved surface. If the size of the particle is small, these effects become very large in magnitude. The change in energy is much higher when the radius of curvature is less than a few micrometers, which is one of the main reasons why much ceramic technology is based on the use of fine particle materials. For properties such as strength and conductivity, the bond area in relation to the particle size is the determining factor. The variables that can be controlled for any given material are the temperature and the initial grain size, because the vapor pressure depends upon temperature. Through time, the particle radius and the vapor pressure are proportional to 2/3 and to 1/3, respectively. The source of power for solid-state processes is the change in free chemical potential energy between the neck and the surface of the particle. This energy creates a transfer of material through the fastest means possible. If transfer were to take place from the particle volume of the grain boundary between particles, then there would be particle reduction and pore destruction. The pore elimination occurs faster for a trial with many pores of uniform size and high porosity where the boundary diffusion distance is smaller. For the latter portions of the process, boundary and lattice diffusion from the boundary become important. Control of temperature is very important to the sintering process, since grain boundary diffusion and volume diffusion rely heavily upon temperature, the size and distribution of particles of the material's composition, and often the sintering environment to be controlled. Ceramic sintering. Sintering is part of the firing process used in the manufacture of pottery and other ceramic objects. These objects are made from substances such as glass, alumina, zirconia, silica, magnesia, lime, beryllium oxide, and ferric oxide. Some ceramic raw materials have a lower affinity for water and a lower plasticity index than clay, requiring organic additives in the stages before sintering. The general procedure of creating ceramic objects via sintering of powders includes mixing water, binder, deflocculant, and unfired ceramic powder to form a slurry, spray drying the slurry, parting the spray-dried powder into a mold and pressing it to form a green body, heating the green body at low temperature to burn off the binder, sintering at a high temperature to fuse the ceramic particles together. All the characteristic temperatures associated with phase transformation, glass transitions, and melting points, occurring during a sinterization cycle of a particular ceramic's formulation can be easily obtained by observing the expansion temperature curves during optical dilatometer thermal analysis. In fact, sinterization is associated with a remarkable shrinkage of the material because glass phases flow once the transition temperature is reached, and start consolidating the powdery structure and considerably reducing the porosity of the material. Sintering is performed at high temperature. Besides, second and/or third external force could be used. Commonly used second external force is pressure, so the sintering that performed just using temperature is generally called pressureless sintering. Pressureless sintering is possible with graded metal ceramic composites with a nanoparticle sintering aid and bulk molding technology. A variant used for 3D shapes is called hot isostatic pressing, to allow efficient stacking of product in the furnace during sintering and prevent parts sticking together. Many manufacturers separate wear using ceramic powder separator sheets. These sheets are available in various materials such as alumina, zirconia and magnesia. They are additionally categorized by fine, medium and coarse particle sizes. By matching the material and particle size to the wear being sintered, surface damage and contamination can be reduced while maximizing furnace loading. Plastic sintering. Plastic materials are formed by sintering for applications that require materials of specific porosity. Sintered plastic porous components are used in filtration and to control fluid and gas flows. Sintered plastics are used in applications requiring wicking properties, such as marking pen nibs. Sintered ultra-high molecular weight polyethylene materials are used as ski and snowboard base materials. The porous texture allows wax to be retained within the structure of the base material, thus providing a more durable wax coating. Liquid phase sintering. For materials which are difficult to sinter, a process called liquid phase sintering is commonly used. Materials for which liquid phase sintering is common are silicon nitride, WC, and more. Liquid phase sintering is the process of adding an additive to the powder which will melt before the matrix phase. The process of liquid phase sintering has 3 stages. Rearrangement. As the liquid melts, capillary action will pull a liquid into pores and also cause grains to rearrange into a more favorable packing arrangement. Solution precipitation. In areas where capillary pressures are high, atoms will preferentially go into solution and then precipitate in areas of lower chemical potential where particles are not close or in contact. This is called contact flattening. This densifies the system in a way similar to grain boundary diffusion in solid-state sintering. Ostwald ripening will also occur where smaller particles will go into solution preferentially and precipitate on larger particles, leading to densification. Final densification. Densification of solid skeletal network, liquid movement from efficiently packed regions into pores. For liquid phase sintering to be practical, the major phase should be at least slightly soluble in the liquid phase and the additive should melt before any major sintering of the solid particulate network occurs. Otherwise, rearrangement of grains will not occur. Liquid phase sintering was successfully applied to improve grained growth of thin semiconductor layers from nanoparticle precursor films. Electric current assisted sintering. These techniques employ electric currents to drive or enhance sintering. English engineer A.G. Bloxham registered in 1906 the first patent on sintering powders using direct current in vacuum. The primary purpose of his inventions was the industrial-scale production of filaments for incandescent lamps by compacting tungsten and molybdenum particles. The applied current was particularly effective in reducing surface oxides that increased the emissivity of the filaments. In 1913, Weintraub and Rush patented a modified sintering method which combined electric current with pressure. The benefits of this method were proved for the sintering of refractory metals as well as conductive carbide and nitride powders. The starting boron-carbon or silicon-carbon powders were placed in an electrically insulating tube and compressed by two rods which also served as electrodes for the current. The estimated sintering temperature was 2000 degrees Celsius. In the United States, sintering was first patented by Duval d'Adrian in 1922. His three-step process aimed at producing heat-resistant blocks from such oxide materials as zirconia, thoria or tantalum. The steps were molding the powder, annealing it at about 2500 degrees Celsius to make it conducting, applying current pressure sintering as in the method by Weintraub and Rush. Sintering that uses an arc produced via a capacitance discharge to eliminate oxides before direct current heating was patented by G. F. Taylor in 1932. This originated sintering methods employing pulsed or alternating current, eventually superimposed to a direct current. Those techniques have been developed over many decades and summarized in more than 640 patents. Of these technologies, the most well-known is resistance sintering and spark plasma sintering, while ElectroCinta Forging is the latest advancement in this field. Spark plasma sintering. In spark plasma sintering, external pressure and an electric field are applied simultaneously to enhance the densification of the metallic ceramic powder compacts. This densification uses lower temperatures and shorter amount of time than typical sintering. For a number of years, it was speculated that the existence of sparks or plasma between particles could aid sintering. However, Halbert and co-workers systematically proved that the electric parameters used during spark plasma sintering make it unlikely. In light of this, the name spark plasma sintering has been rendered obsolete. Terms such as field-assisted sintering technique, electric field-assisted sintering, and direct current sintering have been implemented by the sintering community. Using a DC pulse as the electric current, spark plasma, spark impact pressure, Joule heating, and an electrical field diffusion effect would be created. ElectroCinta Forging. ElectroCinta Forging is an electric current-assisted sintering technology originated from capacitor discharge sintering. It is used for the production of diamond metal matrix composites and under evaluation for the production of hard metals, nitinol and other metals and intermetallics. It is characterized by a very low sintering time, allowing machines to sinter at the same speed as a compaction press. Pressureless sintering. Pressureless sintering is the sintering of a powder compact without applied pressure. This avoids density variations in the final component, which occurs with more traditional hot pressing methods. The powder compact can be created by slip casting, injection molding, and cold isostatic pressing. After pre-sintering, the final green compact can be machined to its final shape before sintered. 3 different heating schedules can be performed with pressureless sintering. Constant rate of heating, rate temperature-controlled sintering, and two-step sintering. The microstructure and grain size of the ceramics may vary depending on the material and method used. Constant rate of heating, also known as temperature-controlled sintering, consists of heating the green compact at a constant rate up to the sintering temperature. Experiments with zirconia have been performed to optimize the sintering temperature and sintering rate for CRH method. Results showed that the grain sizes were identical when the samples were sintered to the same density, proving that grain size is a function of specimen density rather than CRH temperature mode. In rate-controlled sintering, the densification rate in the open porosity phase is lower than in the CRH method. By definition, the relative density ρREL in open porosity phase is lower than 90%, although this should prevent separation of pores from grain boundaries. It has been proven statistically that RCS did not produce smaller grain sizes than CRH for alumina, zirconia, and ceria samples. Two-step sintering uses two different sintering temperatures. The first sintering temperature should guarantee a relative density higher than 75% of theoretical sample density. This will remove supercritical pores from the body. The sample will then be cooled down and held at the second sintering temperature until densification is completed. Grains of cubic zirconia and cubic strontium titanate were significantly refined by TSS compared to CRH. However, the grain size changes in other ceramic materials, like tetragonal zirconia and hexagonal alumina, were not statistically significant. Microwave sintering. In microwave sintering, heat is generated internally within the material, rather than via radiative heat transfer from an external heat source. Other benefits of microwave sintering are a better heat diffusion, less time needed to reach the sintering temperature, less heating energy required, and improvements in the product properties. As microwaves can only penetrate a short distance in materials with a high conductivity and a high permeability, microwave sintering requires the sample to be delivered in powders with a particle size around the penetration depth of microwaves in the particular material. The sintering process and side reactions run several times faster during microwave sintering at the same temperature, which results in different properties for the sintered product. This technique is acknowledged to be quite effective in maintaining fine grains, nano-sized grains in sintered bioceramics. Magnesium phosphates and calcium phosphates are the examples which have been processed through microwave sintering technique. Natural sintering in geology. In geology, a natural sintering occurs when a mineral spring brings about a deposition of chemical sediment at a crust. For example, as of porous silica. A sinter is a mineral deposit that presents a porous vesicular texture. Its structure shows small cavities. These may be siliceous deposits or calcareous deposits. Siliceous sinter is a deposit of opaline or amorphous silica which appears as incrustations near hot springs and geysers. It sometimes forms conical mounds, called geyser cones, but can also form as a terrace. The main agents responsible for the deposition of siliceous sinter are algae and other vegetation in the water. Altering of wall rocks can also form sinters near fumaroles and in the deeper channels of hot springs. Examples of siliceous sinter are geyserite and fiorite. They can be found in many places, including Iceland, El Tatio geothermal field in Chile, New Zealand, and Yellowstone National Park and Steamboat Springs in the USA. Calcareous sinter is also called tufa, calcareous tufa, or calc tufa. It is a deposit of calcium carbonate, as with travertine. called petrifying springs. They are quite common in limestone districts. The calcareous waters deposit a sintering incrustation on surrounding objects. The precipitation is assisted with mosses and other vegetable structures, thus leaving cavities in the calcareous sinter after they have decayed. Petrifying spring at Pamukkale, Turkey. Sintering of catalysts. Sintering is an important cause for loss of catalyst activity, especially on supported metal catalysts. It decreases the surface area of the catalyst and changes the surface structure. For a porous catalytic surface, the pores may collapse due to sintering, resulting in loss of surface area. Sintering is in general an irreversible process. Small catalyst particles and a high reaction temperature are in general both factors that increase the reactivity of a catalyst. However, these factors are also the circumstances under which sintering is occurring. Specific materials may also increase the rate of sintering. On the other hand, by alloying catalysts with other materials, sintering can be reduced. Especially rare earth metals have been shown to reduce sintering of metal catalysts when alloyed. For many supported metal catalysts, sintering starts to become a significant effect at temperatures over 500 degrees Celsius. Catalysts that operate at high temperatures, such as the car catalyst, use structural improvements to reduce or prevent sintering. These improvements are in general in the form of a support made from an inert and thermally stable material such as silica, carbon or alumina.